Okay, in this video we're going to look at example 9 and 10, and this is where you've got to figure out what size nest egg you want for a particular desired retirement income per month. Okay, and for that we're going to look at this formula. The nest egg needed equals annuity payment goal times this over this. Okay, so we've just looked at how to get the annuity payment. If you know your nest egg is $100,000, you can calculate how much that will give you per month. But if we kind of little bit of algebra reverse this formula, if you have a goal in mind, such as example 9, you want to have $3,000 per month when you retire. If you can put the $3,000 in here and calculate how much you need to save, what lump sum of money you need to save, like $100,000, $200,000 or whatever, right? So we'll look at example 9. You plan to work for 35 years and then retire using a 25-year annuity. You want to arrange a retirement income of $3,000 per month. You have access to an account that pays an APR of 3.6% compounded monthly. What size nest egg do you need to achieve the desired monthly yield? Desired monthly yield means the $3,000 paid per month by the retirement account. Okay, so our nest egg needed goes into this formula, right? It can be calculated using this formula. So it's the annuity payment goal, which is $3,000 per month, okay, times, and then we plug in R and T. So what we've got to do is carefully calculate what R and T are, so that we don't make a mistake there. So R equals what? Now remember, R is the monthly interest rate, the interest rate each month. So what is that? The annual percentage rate is 3.6%, which is 0.036, isn't it? So R is going to be 0.036 divided by 12, right? Which is 0.003. Also in this formula we need 1 plus R, so might as well write that down. What is 1 plus R equal to? 1.003. And what is T equal to? T is the term of the annuity, number of months. So there's something we might make a mistake on, so think about that. How do you calculate T? You plan to work for 35 years and then retire using a 25-year annuity. So for 35 years you're working, earning until eventually you have your nest egg saved up, let's say $200,000. And then for 25 years you're retired, you're not working, and this lump sum is paying out $3,000 a month gradually. Okay, each month paying out. So what T do we use? What's the term of the annuity? Okay, so an annuity, once again, is an arrangement that withdraws both principal and interest, and the interest earned each month. Okay, so the annuity means the retirement scheme, you know. So the term of the annuity means how long you're going to be retired for, is what that means. So how long are you going to be retired for? Well, 25 years, but how many months is that? Because we're always calculating in months, aren't we? 25 times 12, right? Which is 300, right? So T equals 300. So we plug in our numbers. So we've got annuity payment goal 3,000 times 1 plus R to the power of T. Now 1 plus R is 1.003 and T is 300. So isn't that 1.003 to the power of 300? Okay, and then subtract 1 all over r times 1 plus r to the power of t. What's that? 0.003 times 1.003 to the power of 300. Does that make sense? And I like to put a parenthesis at the bottom of the fraction for anyone who wants to calculate all of this in one go and just press enter. You must make sure, if you do that on your calculator, make sure to put parentheses around the bottom of the fraction. Okay. So go ahead and press pause now and calculate the top of the fraction and see if we both get the same answer, and then we'll do the bottom together. So we'll do the top first. So if I'm using a simple calculator, right, so I hope you press pause and tried it. I'm going to do it now. So if you're using a simple calculator, right, you got to think about PEMDAS, order of operations, right? Order of operations. So what do you do first? You do parentheses first. So we've got to do the parentheses, and inside there we have an exponent and a subtract. So we would do exponents, right? So the first thing you do is 1.003 to the power of 300 equals that. Then subtract 1. Okay, so you have this number, this whole thing, and then multiply by the 3000. So times 3000 equals that. Okay, so that number goes on the top. Oh, sorry, 436.8.874513, and then calculate the bottom. So press pause and calculate the bottom, and then I'll do it and we'll check our answers. Okay, so I hope you pressed pause and tried it. And again, on the bottom we have an exponent and we have a multiply. So what do we do first? If you look at order of operations PEMDAS, you got to do exponents first, right? So 1.003 to the power of 300 equals that, and then multiply that by 0.003, and that equals this number here. And on my calculator I've got a negative 0.3, so let me just show you what that is. 7.36, right? And that's actually times 10 to the power of negative 3, which means I need to move the decimal point 1, 2, 3 spaces over here, because this number is in fact 0. And I've put in a couple of zeros also, so it's 0.00, right? 0.00736888745. That'll be plenty of digits there, and then we calculate that, right? So 4368.874513 divided by 0.00736888745 equals that number, right? So dividing that, we should get 592.882.238, etc. So what we're going to do is that big number there represents your nest egg, you know. So why don't we round that one to the nearest dollar? Okay, that's a big number there. We'll round that to the nearest dollar. And what do we get to the nearest dollar? Not to the nearest cent, but to the nearest dollar. That would be $592,882, right? Okay, so the next part of question 9 is what monthly deposits are required while working to achieve the desired monthly yield at retirement? In other words, okay, so we want $3,000 a month when we retire. Fine. So that means we have to raise almost $600,000 while we work. So now the question is, how much do we need to save every month in order to get almost $600,000 or $592,000, right? Well, what formula do we have to figure that one out? Have we done something recently? Can you think of anything? So if we look back, we'll find a deposit needed formula, which if you know how much you want to save, that'll tell you how much you need to deposit every month to get the goal or the balance that you're looking for, right? So we'll go to our question now, and it says, what monthly deposits are required while working to achieve the desired monthly yield at retirement? In other words, desired monthly yield, but to achieve, what we want to achieve is, what's that big number we just calculated? What we want to achieve is, this is what we want to achieve, $592,882. Okay, that's what we want to achieve, and this will give us $3,000 a month. So we know that. We know if we save this when we're 65 or whatever, it will give us $3,000 a month for 25 years. Okay, so how much do we need to save each month while we're working to get that? That's the question. So the deposit needed formula is what we need. So deposit, or the monthly, let's call it the monthly deposit needed, equals the goal, and our goal is $592,882 times R all over this thing. Now what we have to do is calculate R, the monthly interest rate, and then get 1 plus R, and of course we have to calculate T and understand what that means. So let's have a look at the question here now. The question is this. So we're talking, if we just take R to begin with, we're talking about an annual percentage rate of 3.6% compounded monthly. And that applies to, like, once we have this in our account and we're retired, yeah, the 3.6% applies to that. But it also applies while we're working. So we're thinking about this in very general terms, that this might in fact be the average APR in an account over, you know, let's say 35 years working and 25 years retired. So that's over the whole 60-year span. The average APR is going to be 3.6%, which of course in real life that's unrealistic. That's going to stay the same. But just for the sake of argument, just for the sake of a calculation, we're going to assume that. So if R of course is the monthly interest rate, and that of course is, as we've seen before, 0.036 over 12, which is 0.003, and 1 plus R is 1.003, right? But T, what's the T in this formula? There's a good question. What this formula is going to calculate, it's going to say, right, you want this amount of money, and it'll figure out what your monthly deposit needs to be, what you need to put into the bank each month to get that. Okay. So what does this T stand for? This T here for the deposit is the number of months that you are saving, basically. Number of months that you're saving money. Okay? And what is the number of months we're saving money in this question? You're going to work for 35 years. that's when you're saving for the nest egg, right? That's the goal, the nest egg here, right? So we're going to work for 35 years, and of course got to times that by 12. Sorry, 12, not 10. Okay, so T equals, if you multiply that, 420, right? So we have T is 420, we have R, we have 1 plus R, so we just need to plug it into the deposit needed formula. So R is 0.003, and it's all over 1 plus R to the power of T, 1.003 to the power of 420, then subtract 1. Okay, so we're going to carefully calculate that and see how that goes. Okay, so 592,882 times 0.003 equals 1778.646, and the bottom is this. So we'll calculate the top and bottom, then divide. So 1.003 to the power of 420 equals 3.5187, etc. Then subtract 1 to get 2.51877. 2.51877 8004. Okay, so then divide these numbers. And we have 706.14, right? 0.1543. 706.1543, etc. So what we've come up with is our monthly deposit needed, and let's round that one to the nearest cent. What would you get if you rounded that to the nearest cent? 706.15. Okay, so here we go. If we deposit $706.15 every month while we work, and that's going to be 35 years, we should come up with this nest egg amount. Okay, and then if we come up with this nest egg amount and we live for another 25 years, it should give us $3,000 per month. All right, so that's the whole idea there.